SwayamPrabha. Digital India. Educated India.
Hello everyone. Today we are going to be going into module 10 and we are going to be talking about one of the most important topics here, large eddy simulation. So we've discussed this topic briefly, especially when comparing it to direct numerical simulation or RANS based approaches, Reynolds average Navier-Stokes based approaches. But today this entire module is going to be a discussion on LES. It is entirely focused on LES or large eddy simulation. So we are going to be looking at covering some brief introduction about LES, what are called the 4 conceptual steps in LES, and we are going to be talking about the filtering operation, which is the key concept here in LES. As you know, LES filters out the Navier-Stokes equations. We are solving for the filtered variables, so it is important to understand what the filtering operation is all about. So we're going to be dealing with filtering in one dimension first, just trying to get a grasp of the concept. Then looking at that in spectral space or spectral representation, we will look at the filtered energy spectrum, just like we looked at the energy spectra earlier. Here we will look at a filtered energy spectrum, because in LES you don't just have a full energy spectra, you have a filtered energy spectrum. The resolution of the filtered fields, the filtered rate of strain, filtered conservation equations, how does the conservation of energy look like, the Smagrinsky model. And so this is one of the key models available in LES, an important model that is used widely, very widely popular. The Smagrinsky model is what we call an eddy viscosity type model or a subgrid scale model that comes about when you filter the Navier-Stokes equations. We'll look at that in detail in this module. We'll look at some limiting behaviors, what the Neowald resolution means for LES, so on and so forth. Okay. So a whole bunch of things to cover. Most of the notes here are from Steve Poe's book. Okay, so let's start with some introduction. As you know, in LES, the larger 3D unsteady turbulent motions are directly represented. What do I mean by directly represented? They are resolved. They are exactly accounted for. In DNS, if you will, in DNS, you would we have seen that even the smallest scale is directly represented. The smallest scale is directly resolved. So that is the Kolmogorov scale. So up to the Kolmogorov scale is directly resolved. So you have a grid that is fine enough to resolve the smallest grid. Now here what happens is in LES, you are having a grid that is only fine enough to resolve the large scales. What happens to the small scales? We model those. So that's what we mean by this. The effects of the small scale motions are modeled. So I believe I've done this before, but if you think about a grid for DNS, this is sort of a cartoon of it, right? A schematic representation, if you will. So this is going to be DNS. This is what a grid is in DNS, and you have all the large scales are represented, of course, and even the small scales are represented. If I want to call that a large scale and a small scale, even the small scales are represented. On the other hand, if I look at an LES, what I'll have is the following. Okay, I will have a large scale that is represented exactly, it is resolved, but a small scale is not represented. So small scale is inside that grid. You cannot see that. So the effect, you cannot just ignore it, the effect of that will be modeled. Physically, that's the explanation. The effect of the small scales are modeled using what we call a subgrid scale model. And an example of a subgrid scale model is a Smagrinsky model. We'll see that in detail. Now here, mathematically, the subgrid scale model comes about in an effort to close some unclosed terms that pop up when you filter the Navier-Stokes equations. Let me repeat that. You have the Navier-Stokes equations. When we filter that, there are some additional terms that are going to pop up. Those are the residual terms that account for these small scale motions that I've drawn. And you will need a model for that because your grid is not fine enough to resolve that. I hope you're understanding. So this is for LES. Now, just for complete closure, let me draw what a RANS model looks like, a RANS grid looks like. Okay, so in a RANS grid, conceptually, you're not resolving anything. All the length scales are modeled. So your grid is this one here. So the large scales are modeled and the small scales are modeled as well. So this is the difference between DNS, LES and RANS. So this is sort of a schematic of it. So what you're seeing here is the accuracy will increase. Obviously, the accuracy will increase as I go from RANS to LES to DNS. The cost will also increase as I go from RANS to LES to DNS. Well, to pay for the accuracy, you will need to spend more, and that is where the computational cost comes in. What I mean by cost is computational cost. So we have seen this multiple times, but I'm illustrating this schematic here in order for you to understand this better on how the scales are resolved and how some scales are modeled in one approach versus the other. So in computational expense, LES lies between these Reynolds stress models and the DNS. What we mean by Reynolds stress models are basically the RANS type models, so also called Reynolds stress models, RSM. And the idea of using LES, the motivation for coming up with an LES approach is we probably don't want to resolve all the length scales. As we saw in the previous module, a lot of effort is spent on resolving the dissipative scales. So maybe that is not what we want. At the same time, we don't want to be as bad, for lack of another word, as bad as RANS, because we want it to be reasonably accurate. We are willing to spend some computational effort on the approach. So we don't want something that is computationally cheaper like RANS, and we don't want something as badly accurate as RANS is. So we want something in between. That is where we have this alternative approach, which is sort of in between DNS and RANS, cost-wise and also accuracy-wise. So that's what we mean by it is motivated by the limitations of each of these approaches. What is the limitation of DNS? The fact that it is computationally very expensive. The fact that you have to spend 90% of your effort on resolving those 10% of that energy in the dissipative range. That's an example. What is the limitation of a RANS approach? It is very less accurate, right? It is the least accurate method. It is cheaper, sure, but it is the least accurate method possible. You're not resolving any scales. You're modeling all the scales. The whole idea, and we discussed this even in the end of last module, the whole idea is based on you are saying that the Reynolds stress is proportional to the mean strain rate, which in many cases may not be even, in most cases won't be accurate at all. So we saw an example of a contraction where the mean strain rate could be 0 if there is no contraction. And that means the Reynolds stress would be assumed to be 0 there. Whereas in reality, if it is preceded by a contraction, there could be a time history associated with the evolution of the strain rate. In that case, the Reynolds stress is not going to be 0 because the mean strain rate, because the strain rate is not going to be 0. It is going to be affected by what happened before that, because there's going to be a time scale associated with the decay of those fluctuations which results in a finite strain rate, which results in a finite Reynolds stress. Unlike in the Reynolds stress models, in the RANS based approaches, we just say, okay, if the mean strain rate is 0, we just say we say that the Reynolds stress is 0, and that is hardly the case. So that's one limitation. And so LES is motivated by the limitations of each of these approaches. Okay, what's the third point here? The large-scale unsteady motions are represented explicitly. Like I said, your grid is fine enough to represent the large-scale motions explicitly, which means LES can be expected to be more accurate and reliable than the Reynolds stress models, of course, because you have a grid that is finer than RANS, as is shown here, and the large-scale unsteadiness is in which the large-scale unsteadiness is captured because of it. Because remember, you are filtering the Navier-Stokes equations. The Navier-Stokes equations are unsteady. You are filtering the Navier-Stokes equations in space. What you're getting, the result, what you're getting is the filtered Navier-Stokes equations which are also unsteady. So this is the beauty of LES, right? You are solving a transient set of equations. Yes, filtered in space, but still a transient set of equations. So the unsteadiness of turbulence is captured to a certain extent. Why do I say a certain extent? Because only the large scales are captured. And considering the fact that we have discussed this multiple times, 80% of the energy is contained within the large scales. 80% of the energy is contained within the large scales. So then if you're capturing that energy, you are probably capturing most of the unsteadiness associated with it. Because most of the unsteadiness is probably associated with the large scales. Most of them, not all of them. Because if you capture all of those, you would approach a DNS, of course. And what LES tries to do is, it tries to capture most of that energy, 80% of that energy, 90% of that energy, not 100%. No way it is capturing 100% of the energy. Only DNS can capture 100% of the energy, which means your grid has to be very fine. LES does not do that. LES only captures the large scale motions, the large scale unsteadiness. So I hope this is clear. So, like we have discussed multiple times, the computational cost of DNS is very high, and it increases as the cube of the Reynolds number, right? So the cost is proportional to RE cube. The computational cost of DNS is proportional to RE cube. So in that sense, it cannot be applied to very high Reynolds numbers. Of course, as discussed in module 9, computers have gotten much faster over the last 10-20 years. So yes, can we do more DNS calculations of higher Reynolds numbers than we could 10 years ago, 20 years ago? Of course, absolutely you could. We still cannot apply it. We still cannot apply DNS to extremely high Reynolds numbers. And even if you did, even if you applied them to high Reynolds numbers, the cost associated with it is so high. It's not like everybody has access to those kind of resources. And in addition to all that, this point is important, right? Which I was saying earlier, just a few minutes ago. Nearly all computational effort in DNS is expended on the smallest dissipative motions. Nearly all. And this is why I brought about the 90-10 rule kind of thing, where you're spending 90% of your computational effort on resolving 10% of the motions, that 10% of the motions being in your dissipative range. So nearly all of the computational effort is expended on the smallest dissipative motions, whereas energy and anisotropy are contained predominantly in the large scales. What do I mean by anisotropy? The directional bias. The directional bias associated with where the flow is going from, right? What direction the flow is. If you have a jet flow, the flow is going from left to right, for instance. The flow is going from left to right. So that means there is that directional bias. Flow is predominantly from left to right. Yes, there are motions in the transverse, in the vertical and the transverse directions. However, flow is predominantly from left to right, in the axial direction, in the direction of the flow, correct? So there is that anisotropy, right? That anisotropy is mostly there in the large scales. According to Kolmogorov's hypothesis, anything in the small scales is isotropic and universal. So we don't know right from left, up from down, back from front, because it is isotropic. On the other hand, large scales, there is a directional bias associated with it. When you look at the large scales, you know where is the flow going from. In fact, you might even be able to identify what kind of flow problem is it. Is it a jet problem? Is it a channel flow problem? Is it a boundary layer problem? Is it a shear flow problem? You might be able to identify that. That is because of that anisotropy, the directional bias. So that's one thing. Second thing is, most of the energy is contained in the large scales. So the premise of LES is, if most of the scales are contained in the large, most of the energy is contained in the large scales, then why don't we just resolve that? Let's not be as bad as RANs where we don't resolve anything. Let's be slightly better, especially since computers have gotten much faster over the last 2 decades. Let's try to utilize that and do LES where we can capture all the large scales, capture all the large scale energy, capture all the anisotropy, because all that is there in the large scale. So let's resolve all the large scales. Whereas the small scales, we will have to make a compromise and model those. Second point, in LES, the dynamics of the larger scale motions, again, which are affected by the flow geometry, they are not universal. We know that from Kolmogorov's hypothesis. Anything in the large scales, they are anisotropic. That means they are not universal. On the other hand, the small scales are universal. These are computed explicitly. They are resolved to the smaller scales. And the influence of smaller scales, which have a universal character, isn't it? According to Kolmogorov's hypothesis, they are universal. That is the universal equilibrium range. Anything beyond the large scale. Remember the energy demarcation length scale, LEI. We'll come across that a lot in this module as well. The energy demarcation length scale, LEI, beyond that, meaning anything less than LEI, are all in the universal equilibrium range. So those are represented by simple models, what we call subgrid scale models. And you will see mathematically, when we filter out the equations, you will see how some unclosed terms comes out. So in RAN's approach, we actually went through this exercise, isn't it? We took the Navier-Stokes equations, we time averaged it in order to get the Reynolds equation. So we did a Reynolds decomposition and then we time averaged it. And then we saw some new terms popping out, right? That was the Reynolds stress term where we needed a RANS type approach in order to close it. Here too, when you filter your equations, new terms are going to come up, which are called the residual terms. And you will need models for that. So approximations for that. That is where the subgrid scale model comes in. So by doing all this, compared with the DNS, the vast computational cost associated with resolving every length scale in DNS down to the smallest turbulent length scale like the Kolmogorov scale, you are avoiding all that. So if I think about the length scale range, I have, say, LEI here, which is the energy demarcation length scale, L0, which is the integral length scale, isn't it? So this is all the energy containing range, ER as we used to call it. And this is the universal equilibrium range, UER as we used to call it. LDI, which would be the demarcation length scale between the dissipation range and the inertial subrange. So this right here is the inertial subrange ISR, and this right here is the dissipation range DR. Remember this? So what you're doing is your length scales, the resolved in LES, are all here in this range. That's it. Somewhere slightly below LEI, and I'll describe why it has to be slightly below. But LEI, technically, you just have to resolve all the way till LEI, technically. Okay? So you're avoiding resolving all the length scales. That's what you're doing. And you're avoiding incurring the large cost associated with DNS. So there are 4 conceptual steps in LES, and this is very important. 4 conceptual steps. The first step is related to a filtering operation which is defined in order to decompose the velocity u into a sum of a filtered component or a resolved component, and a residual component or a subgrid scale component. So essentially, u of xt is decomposed into, just like we did the Reynolds decomposition, this is decomposed into u bar. That's the notation I'm going to be using for filtered velocity. U bar x comma t plus u prime x comma t. This is the residual field or the subgrid scale field. This is the filtered field or the resolved field. That's what you're doing. That is your decomposition now. So looks exactly like the Reynolds decomposition, isn't it? Except the variables have different meanings now. In the Reynolds decomposition, it was with respect to time. We use the angle bracket to represent a time average. So this is the LES decomposition. The Reynolds decomposition looked like this, isn't it? U of xt is average u of xt plus small u of xt. Isn't it? U is equal to capital U plus small u. That's what we had. And so here you are decomposing it into a mean and a fluctuation. This was a Reynolds decomposition. This was a Reynolds decomposition. This is the second one, the one below is an LES decomposition. Now, let's focus on the LES part. The filtered velocity that you get is 3D and it is transient. It is time dependent. Okay, it is 3D and it is time dependent. Here, when you take a mean, of this, it is no longer transient. Right? It is no longer transient because you are taking a time average of it in the Reynolds decomposition. The filtered velocity field, on the other hand, when you filter the velocity field, what you get is a 3D filtered velocity field, which is three-dimensional, of course, and it is time dependent. And this represents the motion of the large scales. Second point, second step. The equations for the evolution of the filtered velocity field are then derived from the Navier-Stokes equations. Once you define the filtering operation, you derive the filtered Navier-Stokes equations by filtering out the Navier-Stokes equations, isn't it? These equations again are the standard form with the momentum equation containing what we call the residual stress tensor. So just like you had the Reynolds stress that popped up when you time average the equations after the Reynolds decomposition, here you are getting a residual stress tensor or a subgrid scale stress tensor that arises from the residual motions. Residual motions means small scale motions. That's your second step. The third step, now that you have this subgrid scale stress tensor that has come up, and you don't have a way to capture that, to solve for that, to calculate that, you will need some kind of model to close it. So that is what we mean by the third step, which is closure is obtained by modeling the residual stress tensor. And the simplest form is what we call an eddy viscosity model. The Smegrinski model is an example of an eddy viscosity model. There are other eddy viscosity models that are out there, but the Smegrinski model is one widely used, a very popularly used eddy viscosity model. But this model is used to close out the residual stress tensor that pops up when the Navier-Stokes equations are filtered. Finally, the fourth step is that the model filtered equations are solved numerically for U bar. Your filtered equations are in terms of U bar. So you are solving for U bar at every point in space, at every point in time. When I say every point in space, it is for a coarse grid, right? It is on the filtered grid. It is on the coarse grid corresponding to the large scales. So this provides an approximation to the large-scale motions in one realization of the turbulent flow. That is what RANS was not able to do. What RANS was giving us was a time averaged, the mean. The RANS was giving us a mean. What LES gives us is it is basically giving us the filtered velocity field for one realization. The filtered velocity field for one realization. That means if you take a DNS field, okay, or if you take an experimental field and you have a velocity field for one realization at every point in space and every point in time, then you filter it. That is the solution you get out of the filtered Navier-Stokes equations. I hope this is clear. So 4 conceptual steps. First one, you define your filter. Second one, you derive your equations applying the filter to the Navier-Stokes equations. Then you close out the unclosed terms, that is the residual stress tensor, using a simple eddy viscosity type model. Fourth one, you solve for the modeled filtered equations. You solve for the filtered equations to obtain the filtered velocity field for one realization of the turbulent flow. So these are your 4 steps. We will cover this again and again and again as we go over different concepts in this module. But I hope this was clear. Thank you.